Okay, let's go over this quick. If we take this shape and we turn it into a net, um, maybe I'll try to highlight so it looks a little better. The top part here, I kind of envisioned as this part, and we know that that is going to be x by 8, and that's the same as the bottom. So I know that these two colors kind of are the top and the bottom. The front side, I can call x by 8, excuse me, x by 30. So this might be the front side, and then this would be the back side. And then the side over here is the larger 8 by 30. And that is the same here. So if we think of this as a net, we can just find the expression for the area for each piece inside. And we don't really have to show a ton of work for this. I understand that if you know the area is 8 times 30, that's going to be 240 feet squared. And then this green one is the same as this one because it's a rectangular prism. And then we have expressions for all the other pieces. Well, this yellow one is x by 8, so that's 8x. This blue one is x by 30. And by the way, this picture, this net is not drawn accurately. That's why I ended up putting the side lengths on here. But then I know that every yellow one is going to be 8x, and every blue one will be 30x. So now I've got the area expressions for all of those, and we know that the total surface area is 1848. So we're going to add all that up. And you can do this by just adding the two 40s together. That's 480. And then let's think of all these x's. I've got 30x and 30x, so that's 60x, plus another 16. So 60 plus 16 is 76x. Now it's a two-step algebra problem. So take 18,480, we're going to subtract, so 1848, and we're going to subtract the 480. And that equals 76 times x, so divide by 76. And we get the missing side length as 18 feet. We didn't focus on this, so alternative way here would be, I know the surface area of any rectangular prism is 2 times the area of the base plus the perimeter times the height. Now, if you do this, it's actually faster, but it's a harder conceptual piece. So you might like this or you might not. The big question is what should I call the base? My advice is if you're going to pick the base, we want the base to be the one that has all the numbers that we know. So I want the base to be the green one because I know I can calculate that base as 240. The P was the perimeter, so it's adding up 8 plus 30 plus 8 plus 30. Now notice, where does that come from? That's the 76 that we had before. And now the height isn't how tall it is, it's what I call the distance between the bases. And once we solve this, notice, algebraically, this is the exact same thing that I get right here that I had here. So these are just two of the same ways of getting the same answer. One is kind of more using a formula. And if you don't choose the missing side as the height, this problem gets a lot more complicated, but yet it will still work. So I just want to show you that. Again, we're not really focusing on the formula. There's only one shape that we're going to really focus on the formula for, and that comes up today. Really quick, I just want to mention that, so yesterday I updated grades at 1:30, and I sent a missing email report to anybody that had a missing assignment, even if you still were working on 12.1 and 12.2. I know you could have turned that in yesterday at 3 o'clock and been fine. I just sent that out so you guys were aware. If you have one missing assignment, you got it turned in. I'll go back and update those grades soon. I just hope that nobody got in trouble from me sending an email. My big concern was the students that had missing projects, Chapter 11 projects, or multiple missing assignments, and I wanted to make sure those emails got out so that you students you knew and parents know as well, and you're working on those to get those turned in. So really quick, just so you're aware, if you count today, we have 12 days left of this trimester, 12 school days left, and it's going to go by quick because I see you every other day. Actually, I'll see you less than that. So let's see, if we count today, we see each other today, we'll see each other Tuesday and Friday next week, and then Tuesday the following week, and March 2nd, which is Tuesday, I will see you 5 more times in person, and that's it. And then we're done with second trimester. Now, that doesn't include Wednesdays or the days that we don't see each other, but please make sure you are getting stuff done and turned in. The trimester is going to come up very soon. Okay, so we're going to jump right into this. Quote for today, real difficulties can be overcome. It is only the imaginary ones that are unconquerable, right? So let's start off with this piece here, and we're going to talk about surface area again. Now, we're going to approach surface area with the same approach we had with prisms and cylinders. Can you draw a net? And from that net, can you then calculate the area of all the sides? It gets a little more challenging when we get into cones, so we'll talk about that. But pyramids, really, it's nothing new. And I like taking the approach of thinking about it from a net, because then we don't have to memorize a whole bunch of formulas. I will show you the formulas, and if you like them and want to use them, you will have time later on to go back and write them down from the notes. All right, we're going to start off and talk about pyramids first. And just to define what a pyramid is, so a pyramid has one base. It has one polygon base. And then all of the sides, notice in this picture here, are triangles. Every time, it's going to have triangular sides. So we then can actually kind of start thinking about what the nets are going to look like. We have some very important vocabulary that we need to talk about. But I want to teach you, if you don't know how, I want to show you how to draw a really nice triangular, actually let's call this a rectangular pyramid. So here's what I would do if I were you. Draw the base first, and the back two lines are going to be dotted. So I have 2 solid and 2 dotted. And then you kind of imagine from the center of your base, just go straight up and put a dot. Okay, that dot is actually the vertex. And the back line is the one that won't be able to be visible, and all the other ones are just straight lines. So I drew my base first. Draw your base first, and then from the center, just put a dot, and then you're basically connecting all the vertices to that vertex up top. The vertex we're going to talk about is also known as an apex. Our book doesn't use the term apex at all. The vertex is just the top. I got to be careful because it could be flipped around, but it's just the point where all the triangular sides meet on the triangle. Now, the next two are very important vocabulary pieces. When we talk about the height is always measured at a 90-degree angle, okay? And it's from the center of the base to the vertex or apex. And they usually put a little 90-degree angle box right there for the height. Okay. Now that's nothing crazy. We talked about height with prisms, but the side lengths were usually the height. In this case, the height, when we turn this into a net, the height disappears, right? The height is not present in the net. And that might be something worthy to note here. I don't have the best spacing. Let's see if I can move this over. Okay. The height is not present in the net. Now, the slant height, we usually use the lowercase l to represent what the slant height is. And slant height is probably a new term. I don't think you've ever used the word slant height, but just from that word slant, it might tell you something. Now notice we have this here. You can see the slant height is actually the height of one of those triangles. So it's slanted. I'm going to draw it in on my shape, but if I was to connect the center, and it's usually the center on a right prism, it's always the center of a side length to the vertex. If you draw that line, notice it's not straight up and down, it's not like the height, but it's actually the height of the one of the triangular sides. And we usually use that lowercase l. So we go L or slant height. All right, a lateral edge is just where two sides come together. So I'm not going to draw it on here, but you can see a lateral edge is just the spot where the sides come together, or the line where two faces meet. We don't do a lot with the term lateral edge. It's the slant height that you really want to make sure you understand what that is today. Okay? What I'd like you to do is draw a net from either the picture that we drew or the picture that's given here. And let's pretend that my picture drawn, or the picture here, is a square pyramid. So draw a net, and then think about how would you find the surface area. Okay, so let's take a look here. If I want to draw a net, we have to start with the base itself, which is a square. And we didn't give you anything crazy for lengths, but you can use congruent markings, right? That's definitely a square. This has got 4 congruent sides. You can even put 4 right angles if you need to. We're really not concerned about the angles for these types of shapes. Now I'm going to try to do this where I'm going to use a red dot to indicate the vertex. And that vertex, this red dot, is really the same distance away from each base. And then if I connect those with straight lines, that gives me the lateral faces, which are all triangles. And since we know that these lateral edges are all the same length, we can use congruent markings here to show that since it's a square, all of these triangles are exactly the same as well. Okay? And there's one other label that we can put in here, and this is crucial. Okay? This is understanding that the red height disappeared. Right? I don't have that height from the center straight up. However, I do have the height of each one of these triangles. So I'm going to label that with L. Ooh, that was not great. But each one of those green lines is considered the slant height, and you can put a 90-degree angle there because we know that this edge and the height, or the slant height, has to be 90 degrees to the base. So we're not going to physically write this out. This is just kind of something to think about. How would you find the area, the surface area? Because it's a square. Now, if this was a rectangular pyramid, opposite sides, opposite triangles would be congruent if it was rectangular, but since it's a square, we've got 4 congruent triangles. So if I think of this as a picture equation, the surface area is the area of the base, which is just the square, plus 4 times the area of one of those triangles. And that's really how you would find the surface area. Just find the area of each piece, add it up. So one thing to think about, there's actually another way to calculate the lateral area, the 4 lateral faces. Instead of doing, because notice they all have the same slant height. So really, if I took the perimeter of this shape times the slant height times a half, that's like doing the perimeter, half of the perimeter times the slant height. And that, if you connect with that, I don't want you to write this down, but if you connect with that, here is kind of a theorem you could use to finding the surface area. It's the area of the base, which is just whatever that shape is, rectangle, square, trapezoid, whatever, plus the lateral area. But the lateral area is the perimeter times the slant height cut in half. So like I said, we're not going to focus on this, so I don't want you to write it down. But if you do connect with it and you like it, you can use it. It's up to you. Okay? These notes will be posted, so you could go back and write this down later. Or if you want to figure out how to use it, you can come talk to me in my office hours and I'll show you a little bit more. Just really quick to give you a visual, this should work out pretty well. If I have a square pyramid and I convert that into a net, visually it's just kind of nice to know what that looks like. And notice the height, the original height from the center of the base to the vertex disappears because we flatten that out. So we lose that dimension of height, but the slant height is still present. Okay? Nothing crazy there. All right. I'd like you guys to draw the net, okay, of this shape. It's up to you if you want to actually draw the three-dimensional shape. Notice the words up here, right? This is a square pyramid. Even though it doesn't look like it, we're going to call that a square pyramid. And I'd like you to draw the net and then see what you can do to find the surface area, or get as far as you can here. I'll give you a couple minutes to work through this. We have. All right. If I draw my net, it does not need to be pretty. I know I have a square base, so I'm going to draw this to the best of my ability. Maybe use congruent markings and just label that each side is 10. And then if I take my vertex and I just kind of put a point out here, since it's a square, I know all these triangles are going to be congruent. And I could go crazy with the markings on the sides, but I'm not really interested in that. What I am interested in is I need to know this height. I need to know that value, but that value is the slant height. And it's going to be the same for each one of these. So my question then is, the 12 is the height. It's not the slant height. This 12 goes away when you create the net. What's missing is if I was to draw the slant height in here, I'm going to use yellow. I don't love this switching colors, but if I pick this side length and I go right to the middle of this side, I got to find the slant height L. Well, notice I've got a right triangle here, and this will always be the case. So if you would like, you could redraw this kind of off to the side here. And the height, which is 12, and the slant height, and half the value, notice this full length is 10. So if this full side length is 10, and this is definitely our center point, the yellow piece from the center point to the edge is always half the value. Okay, so now we've got Pythagorean theorem. Pythagorean theorem, and by the way, this is a triple. You might not notice, but 5, 12, 13 is a triple. If you didn't see that, then you would have to do Pythagorean theorem quickly. and you would find the slant height. So that's what's tricky in these problems, is they don't have to give you all the information. Sometimes they give you the slant height and it's a really quick problem. Other times they don't. But now I know that the slant height is 13 for all of these. And that allows me to find the area of them. So if I want to find the total surface area, I know it's going to be the area of the square plus, and the only reason why I can do this, the only reason why I can do 4 times the area of one of the triangles is because it's a square pyramid. If this was a rectangle, I'd have to find the area of one of these two and one of these two, because the triangles would not be the same if this was a different shape. So be very cautious of that. So what do I know? I know that this area of the square is 10 times 10, or 100. And then I know the area of one of these triangles is 1/2 base times the slant height. So here the base is 10, the slant height is 13, and a triangle is 1/2 base times height. Then I can just multiply those together. Here's the way I would do it. 4 times 1/2 is 2. And then I'm doubling 130, so I should get 260. My final answer is 360 units squared. So even though they didn't give us units, we can still put that on there. Okay. Really quick, I want to show you, I don't want you to write this down, but I just visually, what if I had a rectangular pyramid? What would that look like? The reason why I want to show you this is so you can see that I couldn't use the exact setup here, right? I'd have the area of the base, but then I'd have these two triangles are the same and the other two, but I couldn't do 4 times 1 because they're not all 4 the same, and it's based off of the base on whether or not those triangles will be all equal or just opposite sides will be equal, or maybe even not. Maybe it's a non-friendly polygon as a base. So just be careful on that. Okay, let's shift gears a little bit. Now I want to focus on the cone. And we're not really going to define what a cone is. I'm going to just kind of help you draw it. Here's the way I would draw a cone. So I'd start with like a oval, and I'd do the bottom half solid, and then I'd do the top half dotted, and then from the center point, just go straight up and put a dot. And then you're going to connect those. And then we're going to identify the important pieces. We know the radius of a cone is from the center to the rim. So this is our radius. We know the height is from the center of the base up to the vertex. And then that new word, L, is my slant height. Okay. Now, little challenge for you. Every year I love to see people's interpretation. I would like you to try draw a net for this cone, either one of these, and then think of how you could find the surface area. Okay, so give that a minute or two. Think about what a cone, a net, looks like for a net. So let's think of this. If I undo the cone, we know what the base is going to look like. Our base is the circle with the radius of r. And then I have to undo the cone. Well, think of this. If you've ever had a waffle cone, ice cream cone, if you were to cut that and then fold it and unwrap it, it actually looks kind of like a sector. Now, this isn't the only way to do it, but mathematically it's kind of the best approach. And I just want to highlight a couple of key pieces. So notice this length right here. Okay? This length is the slant height of the cone. And we know that three-dimensionally, when I take a three-dimensional image, the height is not present in the two-dimensional net. So that's gone. We know what the radius is. And then the last piece that's kind of interesting is this length right here. Okay? This green length is the exact same thing as the length around the base. And that is the circumference of the base. Now, it's a challenge to find the area of the sector because we're most likely not given this central angle that we need to solve that. Sometimes we will be, and there's actually an example that we will. However, what I would recommend doing in this case is this is the one formula that I would want you guys to memorize or really connect to. So let me show you first a visual just so you get a better understanding of what a cone looks like. Okay. So here we have a cone, and you can see the height, the radius, and then the slant height L. Now, what if I flatten that? Now, notice this actually is like a cone without a bottom. They got rid of the base. So this is really just the lateral area. And we can see that that's the circumference of the original base. And then the slant height are the two radii. And we could try to find the area if we rearrange these. It's kind of like a parallelogram. I think this is a cool view. We're not going to do this, by the way. I'm just showing you mathematically. There's many ways to solve these. If I increase the number of dissections and then I put them back together, you can see that just creates a rectangle. Now notice this rectangle is the lateral slant height times the length. Look at where the length comes from. It's half of the circumference. So if I took half of the circumference times the slant height, that would give me the area of this sector. I think that's pretty challenging for us to go through. So what we're going to do is this is the only formula you need. So we've got the surface area of a cone, and I usually like to draw a little cone here, is the area of the base. Well, we know the area of the base is just the circle part, right? Plus the lateral area. And the lateral area is that sector. Okay. Now, we know the area of the base is pi r squared. You know what I'm going to try to do? I think this might really help if I can do it. I'm going to try to make this a different color. So you can see where the pieces come from. And that is okay. So the very fast way to find the surface area of a cone, all you need is the radius, so pi r squared, that's the area of the base, plus pi r L. Well, r is the radius and L is the slant height, right? So if it's the same radius as you're given here in the base. But why? Where does this come from? Well, it's really the same as the 1/2 perimeter times the slant height, but pi r L is just the circumference of the circle times the slant height divided by 2. But notice the 2's go away, and I'm left with pi r L. So you don't really need to know this part right here. You really just need to focus on, here's the surface area of a cone. And don't just try to memorize, think about why it is what it is. Pi r squared, well, that's the area of a circle, so that's the base. And pi r L is the lateral area. That's the area of that cone. Okay, I'm going to get rid of this part because you don't technically need it. So the question came up, how do we know the difference between the radius and the slant height? So let me show you, if I gave you a 3-dimensional picture of a cone, okay, where is the radius going to be? The radius is always going to be from the center of the circle out, so there's my radius, and the slant height, the L, is always going to be the length of the side. So that's your slant height. Okay? And then notice they will sometimes give you the height of the cone, even though we don't need the height for this surface area. Right? But as we saw in the previous example, we could give you the radius and the height, and you could do Pythagorean theorem to find the slant height. And that's why the height might be given. Okay, so that's where the radius comes from, and that's where this r is the same. The radius is the same for both parts of the equation. And then the L is always the length of the side. All right, so let's look at an example with using the area of the base plus the lateral area, pi r L. And I'd like you to try this one. You don't even have to write this down. What I want you to do is I want you to find the exact surface area. And what we mean by that is leave pi as in your answer. And if you didn't get the equation from the last slide, here it is. All right, let's go over this one. So if I look at the shape that's given, the center of the base to the rim, that's my radius, and then they give me the slant height already. So I don't need the height because the height is not part of the surface area formula. So all I have to do is take pi times the radius squared plus pi times the radius times the slant height. And since we want the exact answer, we're going to leave pi as pi. So 5 squared is 25. So this will be 25 pi. Now notice, this is the area of the base, right? So I know that this circle has an area of 25 pi. And then the lateral area, which we've always called the area of the faces. In this case, it's not a technical face because it's a curved shape, but our lateral area is 5 times 13, or 65 pi. So the lateral area plus the area of the base is what gives me the total surface area. And if I add that together, I get 90 pi inches squared as the surface area. And sometimes the directions are going to say find the exact answer. If they don't say find the exact answer, then you can do 90 times your pi button in your calculator, and you will get 282.743 inches squared, and that would be our rounded answer. But just make sure you know what the exact answer means versus a rounded answer. Now, I want to show this to you. Don't write this. Please don't write this. I don't think you need it. I honestly think the best way to do these problems is using the formula that's given. But you have to know one little trick if you want to try to solve this using the net. So that's the part that I just want to show you quick. This length right here is the length of the slant height. And I know that if I want to find the area of this base, that's pi times 5 squared, or that's 25 pi, right? That's nothing special. But where does the area of this sector come in? Well, there's one way to do it, is to take the circumference of the base, because this blue segment would also wrap all the way around here. And that is 2 pi times the radius, or that part is 10 pi. Okay? And then, as we saw in this diagram, if I was to take the area of the sector and split it up, so pull it out, and this is why we're using the formula, but this makes a rectangle that actually fills together. So half of the circumference, oops, I don't know why that unclicked, but maybe I'll do it this way so you can see it better. Okay, half of the circumference times the slant height gives me the exact area of this sector. And this is where if I take 1/2 the circumference times the slant height, well, we know the circumference was 10 pi, and we know that the slant height was 13. Half of 10 is 5. 5 times 13 is 65. And notice, if I add those two together, I get the exact same thing I had here. So this would be the way to do it with a net. You just have to know that it's 1/2 the circumference times the slant height, and you kind of have to visualize that piece. I think personally, it's easier to just, for this, memorize the formula. But with that being said, what if I gave you this picture of a net? Now here's another way just to connect with what we're going to do. We're going to do this one together. I'll give you a second to draw this, but find the lateral area of the cone given it's a net. So we know it's a cone, and we know we want to find the lateral area, which means we don't care about, so we're going to exclude the base. right? I need the base to kind of help me out a little bit, but I don't care about the base. I just care about the lateral area. I'll give you a second to write this down. So they ask us to find the lateral area, which means we don't care about the base. And if you wanted to view this as a actual cone, that means we're going to just not worry about the base. And I just want to know what's the area of this wraparound piece here. Or we know that this is a sector of circle. So if I gave you this problem back in Unit 10, Chapter 10, we just need to find the area of the sector. And we know that a sector is going to be its central angle. So this is 98.1 degrees out of 360 has to equal to the area of the sector over the area of, if this was a full circle, so it'd be pi times 11 squared. Okay, so hopefully you remember doing that from chapter 10. Since we're dealing with 98.1, we're going to actually leave this as just a decimal answer. So let's cross multiply. And I'm going to say, instead of 11 squared, I'm going to call that 121 pi. Right? Because 11 squared is 121. And then that's going to equal to 360 times A. And I'll just use my calculator here. So when I multiply 98.1 times 121 pi, I get a pretty big number. And that's equal to 360 times A. So then take this answer, and let's divide that by 360. And that gives me an area of 103.586, and then since it's centimeters, this would be centimeters squared. So I know that the area that this piece of pie or this sector takes up would be that large. Now, there's one other way we could have done this. And I just want you to see this really quick. It's up to you if you want to write it. I know that this is the net of a cone, right? And we know that the net of a cone is the area of the base, pi r squared, times pi times r times L. However, we are excluding the base, right? So I don't need the area of the base. We only need the lateral area. Well, knowing how this formula works, if I take pi times the radius, now this would be the radius of the cone, which is 3, times the slant height, which is 11, that should get me very, very close. Oh, and I want to be careful because this actually isn't surface area anymore, because I got rid of the base. So we would call this LA for lateral area. And then 3 times 11 is 33. 33 times pi gets me very close So notice the answers aren't exactly the same. Okay? And the reason why is this 98.1 is not an exact angle. It's the closest we could get. If we wanted to be more accurate, we would have to find it to more decimals, but it's very, very close. So hopefully that just kind of gives you proof that if you know the angle measure, you can do our chapter 10 ways, find the area of the sector, or you could just take the pi times r times L and find the area of the sector, or the area of the sector, which is the lateral area, using the formula that we just learned. So that's just two different ways to think of it. It's kind of nice to view two different ways in math. Okay, these notes would be posted, so if you ever want to go back and look at them, maybe you really like the idea of these formulas, you can go back and get them. The homework tonight is through the textbook. It's 12.3. That's problem 3, 5, 10, 14, 18, 22, 29, 30. I will say this. When I did the answers to this, I screwed up on problems 3 and 5 because I didn't read the directions. It says find the area of each lateral face. So what is the area of one of the faces? That's all they want for number 3, and that's all they want for number 5. Okay? I actually went and accidentally found the whole the surface area of both of these, so I had to go back and change my answers. Anyways, that's all I got. If you have questions, I'll be available from 1 to 2 today. Otherwise, have a great day. Adios.